Hello everyone. In this video we are going to talk about some common and very important parameters of 3D printing. The first one, which has the most visible effect of your final 3D printed object, is the layer height or the layer thickness really, as well as the nozzle diameter. So when the plastic goes into the extruder of a 3D printer, typically for regular spools, the diameter of the spool most of the time is 1.75 mils. Now, is that the only spool that exists in the market? Absolutely not. We have spools that are thicker or thinner, but this is kind of like the standard. Most of the spools are like 1.75 mil. This is like the gold standard kind of. But the plastic that comes out of the hot end does not have the same diameter. Typically, it goes from this 1.75 to something close to 0.4 mils. Now, again, is that the only diameter of the extruded plastic? No. But this is kind of the most common nozzle that there is. I have seen nozzles from 0.1 mil to 0.8 and more. And of course, the thinner the nozzle is, it makes the overall print time basically a lot more, but it gives you finer print and better surface quality, as well as we talk about the layer height. But bigger sizes of the nozzle will be used for faster prints, for large prints. So this is something that you see in many applications, going from 1.75 to 0.4. And this change happens because the plastic is molten, and also because of the speed at which the almost molten plastic is being pulled into the hot end. Now, one other thing we have to pay attention is when the material is being printed, the thickness of the molten plastic is not going to be the same in all directions. I mean, although we say the diameter of it 0.4, but it's not like really the plastic coming out of the nozzle is perfectly like cylindrical shape. No. What you have is kind of like a little bit squeezed cylinder like this. So you will see this kind of plastic coming out of the nozzle. And then this diameter here, this dimension could be like 0.4 millimeters, while the height of this guy is differently controlled by the printer, right? And it depends on the speed that the hot end moves and builds the layer on the top of each other. So this guy is like your layer height or layer thickness. So it's not equal to necessarily always equal to 0.4. Not that we can't go 0.4, we can. One of the common layer heights for many printers is 0.4 mil. In that case, the shape of the plastic coming out of the hot end does really look like a perfect cylinder. But many times you see, like for example, for Prusa, the default layer height that you see is like 0.2 mil. Okay, and you can go as low as 0.05, and you can go more than that. Okay, you can go more than 0.2 to bigger numbers. And here you can see the visible effect of it, right? So here you definitely have a smaller layer height or layer thickness. Here the layer height is increased, and here is further increased. Of course, the bigger the layer height is, it means your surface roughness is going to be more visible, and you're going to get a rougher surface. But at the same time, it brings down the total print time to a lot smaller numbers, right? So layer height is increasing here, but at the same time, your print time is decreasing. Okay, so it's whether you want it faster or you wanted it to look nicer, or you want a trade-off, right? So this is one thing that I want you to know. So in the X and Y direction on the print bed, what you have is this plastic that goes and creates the object. The thickness of this plastic, as I said, in the X and Y plane, correct? Like this is your Y, this is your X on the printer. The thickness of this material, as I said, is most of the time like 0.4 mil. But if you look at this very same object in the Z direction or any other direction, right, then you see that this guy here is like 0.2 or some other numbers, correct? So this could be, for example, your YZ plane. Z is the direction of the build, the height, basically. So we have to keep that in mind. And use those numbers, consider them when we are designing our CAD part. Before I move to anything else, let me show you that very fast. So here is a simple part on the Prusa slicer, and you clearly see on the top, the print setting, I have the layer height. And the default is 0.2, but I can go anywhere from 0.05 to 0.3, right? So if I go 0.1 mil, which means a good quality, right, detail, and I print a slice really, then you see these different layers here. Let me zoom in further. So you can see these different layers, right, small layers with a distance of 0.1 mil between them, correct? Right, that you clearly can see. But now if you look at the flat surface, like this surface in red, you clearly see the difference. So this surface here in red is a flat surface, only X and Y motion. And you clearly see the thickness of the plastic coming out is way bigger than the layer height. So it's like 0.4 mil, while this guy here is just 0.1 mil. So in this picture, you can see very well next to each other the nozzle diameter or the XY resolution versus the Z resolution. And of course, if you see now, the print time for me is 1 hour 19 minutes with a small layer height. Now if I go with 0.3, which is draft really, so now the surface quality is not going to be as good, but now you see 1 hour 19 minutes is now only 28 minutes. So you clearly see the effect of what? The layer height, and the object definitely looks like a lot rougher than last time. So that's called the layer height and nozzle diameter, which is again nozzle diameter different than spool diameter. Now, before I get into the next parameter, just want to emphasize a couple of things for you. And this needs a video of its own, or several videos of its own if you want to talk about it. But for many applications, you print with a layer height like 0.4 or 0.2 or something, and because you want to keep the print time reasonable, and it does not give you an amazing surface quality, right? So for example, you can see here, this is the part coming out of the printer, right, which is a little bit rough. And one of the things you can do, and many people do, is post-processing the print files. If the appearance for them is of importance, then they do post-process the print files, and the post-processing does depend on the type of plastic. If it's regular PLA or let's say PETG, most of the time the first thing you do is sanding and polishing. Okay, so you try to use a fine, really sandpaper grid number basically, and you try to sand it down and make it smoother. Then the next step for you could be to paint it or use an epoxy resin or something, right? Which you can see here. Or actually, this one is not exactly that. What this one is, you see this owl, is definitely first sanded. And then if the plastic is ABS, then what you can do, you can use acetone. You put it in a container with acetone vapor, and the acetone vapor will create a layer, a shiny, smooth layer on the top of the ABS, and it does change the tolerances and the dimensions of the part a little bit, because it kind of eats out the last layer, the outermost layer of the object. Okay, so you have to see whether the dimensions of the part and how much of those tolerances are important to you, or whether you are allowed to change the dimensions or not. Okay, so we have acetone vapor, we have submerging it in epoxy resin and putting one layer of resin on it. We have sanding, we have painting, and if you want it a little bit fancier and looking better, you can do electroplating, right? You can have a 1 layer or 2 layer coat of metal on it like this and make it a lot nicer. Of course, you have to do it after you polish the surface. So this post-processing, to compensate the effect of rough surface and a big layer height, is something common. If I have time in my future videos, I'll show you samples. But just wanted to mention. The next parameter that is important in printing is called infill. The matter of fact is, not all of the prints that you do are solid. Actually, it's the other way around. Most of the time, the prints are not solid. They are hollow inside. And the reason for that is to keep the print time reasonable. If you want the part to come almost solid like this, definitely the print time is going to go much higher, and I'm going to show you in a Prusa slicer right now. But most of the time you have infill, and that's where the strength of the part is not a big concern, right? You don't want it super solid. The geometry of the outside of the part is the big thing that you care about. So you have infill percentage and infill pattern. There are different types of patterns that you can fill inside the part, like this one that you call the honeycomb pattern, or big ones, small ones. There are star patterns. There are concentric patterns, there are grid and rectilinear patterns, there is triangular, cubic, there are all sorts of things. This one is without any infill. This is just what we call a few shells. There is no infill here, so none, basically. So there are different types of infills, and so far, based on many researches, it turns out that this rectilinear one, this guy here, is really the one that gives you the better strength and also faster print time. So I typically go with rectilinear. Again, it makes the printing faster and also makes it a little bit stronger than the other patterns too. So this is what I recommend to you, rectilinear, or the bigger version of it you might call the grid. Okay, these two are the best. And then we have the percentage. How much really, right? How much of the percentage do you want to be filled? So do you want like 10%, 20% infill? Do you want 100% infill, which means completely solid? So the percentage and the pattern will affect the strength of the part, but not really the appearance of the part from outside. So if I want to show you here as an example, here is the part, and I can go under print setting, go to infill, and I can change it to anything I want. Like for example, for Prusa, most of the time it's Gyroid, which is not really the best one. You can change the infill percentage, right? And let me go back to rectilinear because that's what I use. And I use 20%. And I slice it. Now you clearly don't see any of that rectilinear pattern here because it's inside. So if I bring down the number of layers here on the left, then you should be able to see that pattern clearly. right? You see that interior pattern, which is hollow, right? And this is at 20%. Now, if for the same pattern, I increase it to like 60%, right? Now you clearly can see that although still hollow, but the amount of hollowness is reduced significantly. And if you look at the time, 60% is 40 minutes, while 20% was only how much? 29 minutes. Okay, so it does matter. And if I go fully solid, 100%, now it goes to 52 minutes. Now there is no infill. The layers are just put next to each other without any gap between them. Okay, so the bigger percentage means more print time. And you can change the type, as I said. So if you remember with 20% rectilinear, it was 29 minutes. Now if I change the pattern to gyroid, which is, as I said, the common thing in Prusa, go back and slice again, now you see it's 32 minutes. So not only gyroid is not as strong as rectilinear, it also, you can see here, it also takes a little bit more time to print. Okay, so this gyroid pattern is not what I suggest to you. You can have the triangular one. You can have the, let me just show you a few more. You can have the concentric one, right? And here is the honeycomb for you. Okay, so this is the infill percentage and pattern, and what I recommended for you to use. The other thing is, outside each one of these infills, as you can see, the exterior layers, the solid layers that we have, they are fully solid layers, which we call shells, or they must simply be just called layers. So shells or layers is the number of fully solid layers around on the exterior layers of the object. And you can control the perimeter shells, the top shells, and the bottom shells separately. Of course, the more shells you have, it takes a little bit more time to print, but definitely gives your part a lot more strength. So if you want to print something, even though it's not really a functional part, I still absolutely recommend you go with a minimal of 3-4 shells. Okay, for many software, the default for many directions is like 2 shells. I still don't think it's good enough, because remember, the thickness of the plastic coming out is only 0.4 mil. So 2 shells means 0.8 mil wall thickness, and that's not really strong. By all means, try to avoid one layer. I see many people, when they want to print, they use one layer. Unless you really want it for that reason to be very, very thin wall, which is sometimes even a little bit transparent, because you can see the light through it to a good extent. There is no reason for something to be one layer, because even with the smallest contact, that one layer 0.4 mil wall thickness will break. So here, let me show you. I have 20% infill, and my print setting, let me put it back to rectilinear, and I go to layers here, and you see typically Prusa suggests different number of layers for different directions. Like it says for top, go with 4 layers, for bottom for 3 layers, perimeter 2 layers, right? So let me make all of them to be 3 shells, and you can see this is the appearance, right? You see the layers, the shells are shown with orange and yellow, and then inside of it the infill is shown with kind of dark red, right? So you see clearly there is 3 shells, right? If I want no infill, then it's just going to be those 3 shells. Everything else is going to be just like completely hollow out, as you can see here, right? So feel free to change the number of shells, but definitely the recommendation is 1 layer is absolutely a bad idea, right? Because your part is going to be extremely thin. Okay, a part like this will easily break. We have the support material. Support is important if you print an overhang. And you can change the angle of transition for the overhang, because not every overhang necessarily needs a support. There is an angle that you typically determine in the software. The default of it is 45 degrees. And when this overhang that is extending beyond the object, like this guy here, you cannot print the layer of this on the air, right? You have to have something beneath them to carry the weight of those layers, and that's what you do. You call it the support plastic. Now, the transition in many software, the default transition angle is 45 degrees. It means if the overhang is having an angle more than 45 degrees, let's say here, something like this, 20 degrees, 30 degrees with respect to the vertical direction. If it's something like this, then because of a lot of overlap of each layer with the previous layer, for this one where this angle is like 30 degrees, for this one you can probably get away with not having a support. Each layer has a lot of overlap with the previous layer, as you can see, and that lot of overlap will allow that overhang to be printed without anything below it. Because at the end of the day, you have to get rid of the support material. You have to break it, you have to dissolve it, right, and get rid of it, because that's not a part of your model. So most of the time, as I said, the transition angle is 45. Less than 45, you can get away with the support. More than 45, it is recommended to do so. But again, you can change that transition angle in your software. So here, if I make a mistake and I print my part upside down, right? So I come to this part and then I make it upside down like this. Now, definitely, all of this head, most of it, is going to be just up printing in the air. And if I don't put a support here, that's not a good idea, right? So here, you see it says support, I say none. If I do that, then during the print, you easily would have this plastic being printed up in the air and it falls under its own weight. And you have a completely deformed, messed up print, really. So it's a good idea to say yes, support it as long as it connects to the build plate or everywhere, right? Let's say I say support it everywhere that it needs. And now you can see this green support plastic is added with low density, and it's not all over the place. Some places it determines it's too close to the base cylinder, but the rest of it does need this low density plastic in green. And this is the plastic that you can see clearly. It has a lot lower density than your own object. Let's say here I say 30% and reslice it, right? Then you clearly see a lot lower density on this support, and you can easily peel it off, break it with a long nose prior, or if it is a printer that has dual nozzle, so one nozzle prints plastic of model, the other one here, like this brown material, prints the support. You can put it in a solvent and get rid of it. Or, as I said, you break it. So that's the other thing that we have called support plastic. And there is a bunch to this support. As I said, the transition angle of it, whether I should change my support to support everywhere or just for support enforcers or on the build plate only, correct? Or none. So here, let me show you in another model a couple of those settings, although as I said, I will have a separate video on Process Slicer software, but you see here, if I say I want support only on the build plate, right? This is what you will get. Only the part of the material that for which the support comes into contact with the build plate will get supported. But if you say everywhere, then you'll get in a little bit more places, right? You clearly see here for the head that for this the support does not rely on the touch the print bed. Also get support material here, this plastic in green, right? Or you can say none, or you can say for support and forces. What is support and enforcer? I'll show you in a separate video, as I said, on Prusa Slicer. If you go to the print setting under support material, you can see the default angle of Prusa for overhang is 55 degrees, and you can change this angle, but this is that transition angle I was talking about. Okay, so that is about the support, and we'll see more of that in future videos. The other things that we need to talk about are raft, brim, and skirt. Raft is basically a kind of support that is at the bottom of the part, and it's only a few layers thick. What it does, it helps the part being stabilized on the print bed and stick to the print bed better. Okay, so it's like an initial bottom layer, and the part is going to be placed on the top of those initial layers, and again the goal of them is better sticking to the bed during printing and more stability, especially if the part is tall and it has a narrow bottom surface. Okay, it helps with stabilization, and you can see that here, right? What you can see here, I have no support, infill, and something. If you print in Prusa, all you see at the bottom layer is what we call a skirt. This is not raft or brim. This is the skirt that you see these several layers right next to each other, 3 layers around the circumference of the part. That is what we call a skirt. That's not the raft. And a skirt is just 3 layers, and they are not even on the top of each other. They are just on the XY plane, so there is no Z elevation here. All it does is just to prime the hot end or the nozzle, so allowing the plastic to come out of nozzle and have a good flow of plastic before the main print starts. So this is basically all it does, is to make sure that you have good flow, and if there is any remaining plastic from other prints with a different color or anything, right, they get to stick to the bed before they come and affect the main print. So that is the skirt. And if you make it attached to the object, you call it the brim. So this middle one here is the brim. Brim is like a skirt, but it is attached to the object. It doesn't go below the object like a raft does. Rafts are several layers, so you have Z height here, more than one layer, that goes below the object for stabilization. Brim is only flat layer, okay, or there is only one layer height, but they are attached to the body of the print, and not only they can help priming the printer and cleaning it up, the nozzle, they can help a little bit with the stabilization too. Okay, so brim is somewhere between a raft and a skirt. It kind of serves the purpose of both to some degree. I would say the purpose of a skirt to a good degree, the purpose of raft a little bit, not as much, because it does not extend below or beneath the part. It's just like some extra holding and only one layer height around the object to increase the surface basically the bottom surface, and serve more for a stabilization really than sticking to the bed. A little bit it helps sticking to the bed too. So what you see here naturally is a skirt. If you want, you can check this item, and now it will convert it to brim. As you can see, now it is attached to the object, right? And it is really mostly one layer. It has a little bit extra layer here, so it's not perfectly flat. You see some extra layers in some offset from the object is created, but mostly it's flat. And if you want, you can go to the support and add raft layers. These are the ones that go below the object. So I can say go and create 3 layers below the object, no brim, just create raft, and then you see the object will be printed on the top of the raft, which you here can see in a green color, right? The next topic is bridging in 3D printing. So bridging means print overhangs, but without adding support material underneath them. How do you avoid the plastic basically sagging down? By moving very fast. Okay, so if you move very fast and apply basically appropriate amount of tension in the molten plastic, you try to avoid sagging. Now, you clearly here can see if it's a short distance that I'm trying to bridge and go very fast with appropriate tension without support, I don't have much of a sagging. You see, I can get that overhang printed without support material. Now, as the length of the bridge, right, gets bigger and bigger, now you see the sag is showing itself, and the plastic that is molten without support is falling down a little bit and sagging. So there is some limit really on how much you can bridge, okay? And that depends on the printer, that depends on the cross section that you are printing, that depends on the plastic and so on. So there is no magical number or formula I can give you, but just remember that if it's a small, short distance overhang, right, or material up in the air, you might apply the bridging and try to avoid putting support. And you might say, okay, what's the point if I can add support and avoid any sags like here? Why should I do that? And the answer is, for example, if you look at this part that I designed and printed, here it is like an assembly. This is this eagle on this pin, and the pin is inside this kind of support or bearing in the main keychain or loop. And I have printed this whole thing in one piece. And when you print this and you lay it flat, okay, so I put the back side of it on the printer, then there's bearing areas, right? If you print plastic and you print it all as one piece, as I did, then the shaft is going to be attached to the interior surface of the hole, and then you cannot achieve the rotation here. So inside here, inside this area that you can see, inside this area, if you look at it, there is this hole, right? That is the bearing hole, and there is this shaft that is inside the bearing hole, like this. There is some small gap between them. Now, as I said, if I don't do bridging, then between the hole and the shaft, printer would lay plastic and then makes the connection between them solid so the shaft cannot rotate inside the bridge. But if it doesn't do that, and when it wants to go from one side of the hole to another side, right? So here, it is going like from here to here. It is printing this top area, for which there should be some support to hold its weight. If it doesn't and just go very fast, does some bridging very fast, then what it does, it makes the interior of this hole completely empty. And then the shaft can be printed. Also, when you print the shaft, below the shaft, between the shaft and the hole here, there should be some support too. But again, if it does it very fast with bridging and leaves nothing behind, then what you can do is you can have what? You can have a functional bearing, and you can print this whole part in one piece instead of two pieces, and then kind of assemble them together, which is not really easy for plastic parts like this. Okay, so you clearly see I printed it completely flat, so this eagle was completely facing this way, right? This back surface of it was on the print, and now it is definitely what? It can definitely rotate about the axis. Okay, so that's the good thing about bridging. And you know, always removing support material can lead to breaking the part as well if you are a little bit rough with it. And at best, it can leave some scars on the surface that you have to post-process and remove. So it has applications from making assemblies printed in one simple part and making something like bearing and so on, then avoiding supports, which makes cleaning and post-processing a lot easier. So that's bridging. The last topic I want to talk about is retraction. And retraction is what? When you have this extruder, and this extruder is laying out your molten plastic. The thing is this, that when it is laying this plastic, you know, you have this motor here, and this motor is bringing in the spool, correct? And then using two gears, the idler mechanism and the gear that is attached to the motor, it brings it to the heat sink and heat block here, right? And then put down the molten plastic on your object, on your print bed. The problem is this: when you don't print temporarily, you're going from one point to another, and your goal is just to move the hot end from one point to another. Your goal is not to lay down plastic. What's going to happen? Like here, I print some cross section here, and then I want to go to the same Z layer and print the plastic here, correct? When I do the transition from here to here and then back, if I don't retract the plastic back into the nozzle, right? So this motor is constantly driving this way and bringing this plastic in. If I don't stop the motor and temporarily reverse the motor so that this plastic that is coming out, it goes back up into the hot end. If it doesn't do that, then during this transition, you're going to see all of this extra plastic that are laid down on the way of the transition without us really intending to do so. And this is the thing we call stringing. Okay, so each printer has the capability to retract the plastic at some speed back while it is just transitioning between 2 points. Between them, your goal is not to lay down any plastic and get this nice clean print. So only print here. In between these two, you do retraction. When you get there, you lay down the plastic. Again, you go back, you do retraction. Okay, and the speed of the retraction, the amount of retraction, they are some of the parameters that you can control in a slicer software like Prusa or any other thing. So if you see this kind of behavior, stringing, the goal is to apply more retraction, and the speed of it, the amount of it, and avoiding this kind of stringing problem. Okay, so hopefully review of these important parameters of 3D printing give you some foundation. So when we go in the next video, and I'll train you on Prusa slicer software, and I show you how to set up each and every one of these parameters. I did to a good extent some of them in this video. Then you have an understanding of what I'm really talking about. So hopefully this video was useful to you, and I will see you in my next video. Thank you so much.